Hello student and welcome to the Thermochemistry chapter. In this chapter we will be talking about energy. Energy is defined as the capacity to do work. So it is the force acts through a distance or a transfer of heat, which are just different forms of energy. The SI unit for energy is the joule, and we also in the US use the calories. Now please pay attention that 1 calorie equals 4.184 joules exactly. So this is exact, means it's defined and there is infinite number of sig fig. A potential energy is the energy stored due to a position. So, for example, when we are elevated, like the person on the bike in this picture, when you will store energy due to elevation. This is why once you start going, you don't have to paddle because you have already stored energy that is transferring itself into kinetic energy. Another form of potential energy is the chemical energy, which is the energy stored within the chemical bonds. An example will be food. We eat food to get energy, but the energy in the food is potential energy. It's stored in the chemical bond that we have to break during metabolism. Also, the energy, for example, in the gas that we use to run our cars with, the energy is potential because it is stored in the chemical bonds of the molecules of the gas. Kinetic energy is the energy of motion, and thermal energy is an example of this because thermal energy is associated with random motion of particles. So, for example, the difference between cold water and hot water. In hot water, the water molecules are moving very, very fast, which is transferred to the thermal energy. Energy is also a state function, and this is a very, very, very important definition that we will be using a lot when we talk about energy. And by a state function, by what we mean is it depends on the initial and the final state, but not the path. So what matters is where do we start and where do we end? What happens in the middle does not really matter. So here is an example. If you guys look at this picture, you will see that there are two hikers who wanted to go and hike all the way to the top of the mountain. The hiker with the blue path took a shorter path but ended on the top of the mountain from the bottom, started at the bottom and ended at the top. And the hiker of the red path also started at the same point at the bottom and ended at the exact same point at the top. Now remember, we do gain potential energy due to elevation. Since their start is this and end are the same, whoever took a longer path, a shorter path, that doesn't matter. The potential energy stored due to elevation is the same because the initial and the finals are the same. So the change of energy, which is the amount of energy in this case, acquired, the potential energy acquired due to elevation will be the final minus initial. And since the final and the initial are the same for both hikers, they both got the exact amount of energy. Now, not only energy can be a state function, but also pressure is a state function, volume and temperature, because what matters is the change. What is the final and what is the initial? When we look at the first law of thermodynamics, which is the conservation of energy, energy can be converted from one form to another, but it can never be created nor destroyed. So what happens to energy? It can transform from one form to another, but you cannot create it out of nowhere and you cannot destroy it as well. Heat as we said, is a form of energy, and it is what we will be focusing our study on in general chemistry. There are processes that do release heat, and we call them exothermic processes. So, for example, when I react oxygen gas with hydrogen gas to make water, energy will come out. This is exactly why, for example, we have to store hydrogen gas in special cylinders that are really metallic with thick walls, because we don't want them to be mixed with oxygen, because any spark can create that reaction that forms water, but most importantly energy, which translate in real life into explosion. So that makes this reaction to be an exothermic reaction. It releases energy. Energy is a product of this reaction. Also, when I have water vapor and I condense that into liquid, energy will be released. That's why steam burn are very dangerous, because when a steam touches the skin, then it does condense into water and releases that huge amount of energy that can burn the skin. The opposite of exothermic processes are the endothermic processes, and these are processes or reactions that do need heat to occur. For example, if I want to decompose mercury 2 oxide into mercury and oxygen gas, I need to heat it. Once I heat it, this reaction will happen, so that reaction is endothermic. If I want to melt ice into liquid water, then I need to give ice energy. I need to warm ice. So now energy is a reactant in this case. And I also want you to pay attention that we are using the word reaction and a process, because reacting hydrogen with oxygen, that's a reaction to give me water. But condensing vapor, that's a process. So we are really covering reactions and processes, because both can be either exothermic or endothermic. Enthalpy is the term we use to express the heat change of the reaction. So as I have just discussed, reactions can either produce heat or absorb heat. And I use the change of the heat to understand if heat was given off or was it absorbed during a certain reaction. So delta H is the amount of heat that either was given off in an exothermic reaction or absorbed in an endothermic reaction. Delta H, now in a reaction, what is final and what is initial? Final is the product and initial are the reactants. So if I have the potential energy of my products and the potential energy of my reactants, the difference between them is the change of the reaction. So if the reaction is exothermic, it means that the heat of the products was lower than the heat of the reactants. So if this is my reaction here, and I have, this is the heat, so if this is energy going up this way, and these are my reactants and these are my products, which means the potential energy of my product is lower than the potential energy of my reactant. In the process of reactions, we go from reactants to products. So we go from high energy to low energy. That difference in energy has to come out. Therefore, it's exothermic. But since a product, which is my final, is lower than the reactants, which is my initial, then delta H here will always be a negative value. All good? All right. Now the opposite is an endothermic process, and in this case I have the opposite here. if this is the energy going up, and these are my reactants, and these are my products, right? And if I want to go from reactant to products, then I need to put heat in to have this process. And since the products, which are my final, are higher than reactants, then delta H here will always be positive value. Now, how do we write a thermochemical equation? If delta H is negative or positive at a constant pressure, that's a question that every chemist is interested in knowing about any given reaction. So here is a process. If I melt ice into liquid water, delta H is 6.01 kilojoule per mole. What does that mean to you? Let's read that together. This is a balanced equation. What the equation is suggesting that every mole of ice need 6.01 kilojoule to be melted into 1 mole of liquid water. Now, why did I say need? Because delta H is positive. And what does that mean to me? It means that this process is endothermic. Okay. Now, it also means that heat is a reactant. I needed heat for this process to take place. So I can actually write it down in another way and say that 1 mole of ice needs or react with 6.01 kilojoule to be melted into liquid water. Here is another reaction. When I burn methane with oxygen or combust methane with oxygen, I'm going to get carbon dioxide and water. Look at delta H, negative 890.4 kilojoule per mole. What does that mean? It means that every time I am combusting 1 mole of methane to react with 2 moles of oxygen, 1 mole of carbon dioxide will form, 2 moles of water will form, and 890.4 kilojoule will come out. And the reason why I say will come out, it's because I have a negative sign, and the negative sign says exothermic, right? Heat is a product in this case. Because it's a product, I can also write it as a product. And pay attention here, when I wrote it, I'm not writing negative, because in this case, the heat, the product that comes out is 890 or 890.4 kilojoule. When I write delta H, it's the change, and the change on the heat is negative 890.4 to indicate that this is an exothermic process. Now, if I want to write delta H for any reaction and interpret that to give me more information, first thing first, you need your equation to be balanced. Per mole in delta H refers to the stoichiometric coefficients, meaning, let's put this example again. When I say 890.4 kilojoule came out, it came out per mole based on the reaction that it is representing, meaning 1 mole of methane, 2 moles of oxygen, 1 mole of carbon dioxide, 2 moles of water. Every 2 moles of water will give out this energy. Every mole of methane will give out this energy, and so on. If you reverse a reaction, you change the sign of delta H, but not the magnitude. Why? Because let's think about it. I need heat to melt ice into water. But when water freezes, it will release the heat. which means anytime I look at the reverse reaction, delta H sign will change as well. So let's look at this diagram together. If I go from methane and oxygen to carbon dioxide and water going this way, right? This is now final and initial. That will give me delta H of negative 890. But if I go the reverse, let me write this down for you for a second here, which means if I go carbon dioxide reacting with 2 water to give me 2 oxygen gas and methane gas, right? Now delta H now will be 890 positive, because now this here in the reverse direction, this is my initial and this is my final, and final minus initial in this case is the opposite sign. As I said here, if I am melting ice, the process is endothermic, but if I am freezing water, which is the second line here, the process is exothermic. If you reverse, you have to reverse the sign of delta H. The magnitude doesn't change because it is the same difference between the initial and the final. It just depends on who is the final and who is the initial in every direction. We must specify the state because every state has a different potential energy. For example, melting ice will demand 6.01 kilojoule per mole, but evaporating water, 1 mole of liquid water, will demand 44.0 kilojoule. 2 different processes. It's very important that I distinguish, am I melting ice to liquid or am I evaporating liquid to gas? If you multiply an equation by a factor, you have to multiply delta H by the exact same factor. So now, let me read this for you to be clear. If I say that melting 1 mole of ice demands almost 6 kilojoule, then it does make sense to you if I told you, okay, if I need to melt a mole, I need 6 kilojoule. How many kilojoule do I need if I am melting 2 moles? You immediately will tell me, well, if 1 mole takes 6, then 2 moles will take 12. So what you really did, you multiply delta H by the exact same factor. Let's practice the writing the delta H and how can we use it to learn about chemical equation. How much heat is evolved when 74.6 grams of sodium is converted into sodium hydroxide and hydrogen gas according to the following equation? This is a balanced chemical equation. It is suggesting that 2 moles of solid sodium reacts with 2 moles of liquid water to give me 2 moles of sodium hydroxide solution and 1 mole of hydrogen gas. Delta H is negative 367.5 kilojoule. So it's an exothermic reaction. I know a relationship, and this is very important here. They are asking about heat. Change color here. They're asking about heat how much heat when giving you grams of sodium. Now the relationship that you know is coming from this balanced chemical equation, and it comes from energy and amount of moles. So what you really know that every 2 moles of sodium will give 367.5 kilojoule. That's the negative here is the sign to show that it is exothermic. But if I am talking amounts of heat, I can just say the amount of heat as a numeral value. So I have a relationship between moles and heat, but they gave me grams. So what I do, I'm going to take 74.6 grams of sodium and multiply that by the atomic mass of sodium. So I'm going to say, oops, sorry for that. Let's just go back. 74.6 grams of sodium times 1 mole of sodium has an atomic mass of 22.99 grams of sodium. And now I can do the following. I can say, I'll write two ways and I will explain to you what they mean. I can say negative 367.5 kilojoule for every mole of sodium. And if I do the math here, taking into account that I need 3 sig fig, I'm going to say 74.6 divided by 22.99 multiplied by 367.5, and this is where 2 moles of sodium and divided by 2, that's gonna give 596, and this is a negative kilojoule. Or I can also say 74.6 grams of sodium multiplied by 1 mole of sodium has an atomic mass of 22.99 grams of sodium times there are 367.5 kilojoule for every 2 moles of sodium, and I can say 596 kilojoule evolved. Let's just use the exact same word, evolved or released. So what's the difference between them? It's the exact same thing, but if I put the negative sign, it is understood that it is released, right? Exo. If I don't put the sign, I'm just using it as a numeral value for energy, then I just said it, 596 kilojoule evolved. So the negative sign means evolved. If I don't put it, I have to put the word evolved. Okay, let's look at this question. If 6.47 times 10 to the power 3 kilojoule of heat is produced according to this equation, how many grams of oxygen must have reacted? So this time they gave me a balanced equation, they gave me delta H, and they gave me the amount of energy produced. And they want me to know how much oxygen must have reacted to produce that amount. Okay, then I ask myself, do I have any relationship between energy and oxygen? Yes, I'm going to have it from the balanced equation. 3013 kilojoule evolved for every 5 moles of oxygen. Now I have energy, so I'm going to start with energy. 6.47 times 10 to the power 3 kilojoule. Now let's use a conversion factor between energy and oxygen moles. I can say there are 5 moles of oxygen gas that are reacting to produce 3013 kilojoule. Now that I have that, I can take the moles of oxygen and say there are 32.00 grams of oxygen gas for every 1 mole of oxygen. Now when I do this math, it will be 6.47 times 10 to the power 3 and multiply this by a 5, divide by 3013, and then multiply this by 32, and the answer with, I need a 3 sig fig, will be 340 4 grams of oxygen reacted to give that amount of heat. All good? This will be it for this lecture, and I will see you in the next lecture talking about calorimetry.